Hi, my name is Cheren. I'm a software engineer with Wolfram Research. Today I'll be talking about two important data formats in Wolfram Language, CSV and PDF, updates to them, and building high-level applications.
Hello, everyone. My name is Cheren. I'm a software engineer at Wolfram Research. Today I'll be talking about some updates to two very important formats, PDF and CSV. And I'll also show some ways that we can use these formats to build high-level applications. To start out, I'm going to say I had a little technical difficulties just now. Wasn't expecting my kernel to die when I plugged in the computer, so let's hope that we can still go through this smooth. So to start, we have some changes that we're making at the import and export. Sure. And the volume. All right, is that a little better? Good. So in the next version, we have built some mechanisms into import and export that provide strong low-level access for specific formats, but give these formats the mechanism to make them consistent between formats. So coming right away in 12, we have a lot of formats already using this stuff: CSV, TSV, Excel, FITS, and then the chemical formats that we are introducing or modifying. And right now the plan is we have a lot of old formats that aren't using this stuff that we're going to continue to optimize to use these things. We also plan to introduce these with any new formats that we release that have, parts of the file that you could access. In particular for CSV and TSV, we have greatly improved partial access in terms of supporting spans and any kind of span, whether it's from the end of the file and in any step and in any direction. These parts also, your CSV data could also contain headers, which you may want to strip or interpret with your data sets. We improved the processing for this, as well as the interaction between taking the parts of files. Excel has the exact same support going on, with the addition that you can also query by sheet because it's a list of 2D sheets. We're also introducing some metadata elements that are particularly useful to you so that you can get the number of sheets or the size of the sheets without actually having to import all the data. I'm also proud to say that every single bug that was reported in 11.3 is fixed for 12. No bugs. So for CSV and TSV, with partial access, you already know that we have always supported, ragged data, and CSV has a structure where it doesn't necessarily have the same number of columns in every row. So if we have this ragged data right here, we can see, it increases by 1 for each row. Now, any span that you can throw at it is going to work properly. And not only this, but the dimensions that you're asking for are always going to be honored. So in particular, if you ask for something where it's ragged and the data isn't there, we're going to tell you that you asked for some data that was outside of the range, but we're still going to give you exactly the structure and form that you were looking for. For Excel, this also means that, and this is brand new, that you can search either by the index or by the name of the sheet to grab the sheets that you're looking for, and then we can say just grab the first 3 rows. And just a quick example of these brand new elements, we have sheet count and dimensions, which returns simple information about your spreadsheet as efficiently as possible. So the next part of the talk, I want to give some details on kind of the underlying way that CSV works and how we can use this to preserve the contents of our notebook so that we can get back to it later. So first off, let's talk about what happens with CSV data as you throw any random expression with different depths. So with 0 dimensions, like just this string hello, you can import this back, but you're always going to get a table back. CSV always assumes that your data is a table. Of course, you could take the parts and then get back to your individual string. Now, because in your list, every single element is considered a row, when you pass a one-dimensional list to CSV, every single element is interpreted as a row, so you have a column vector basically as your result. Now, your data might not have a consistent depth. In this case, where you have some elements that aren't wrapped in their vector, but you also have a row that does have multiple elements, CSV automatically fills in the data so that you always have something rectangular. We have control over this. Now, if we try to import it and tell it that we don't want it to fill these rows, we find that we still get this data. Well, that's because the data was actually there. Look in the second column, you actually see that there is a physical element there. It's just empty. You can control this when you're writing to the data. So if we export with fill rows to false, we get exactly the length that we were looking for in each row. Then, when you're importing, you can do the same thing and put them back. So whether the data was there or not, you can tell it what you're looking for. For data in 2 dimensions, this is the case that you've all seen for any standard CSV. For higher order dimensions, things get a little weird. Now, we do have to understand the limitations to the CSV format when choosing it as a medium for our data. If we want to preserve that some of these rows were at no depth, but these other ones had a depth of 1, this isn't possible looking at the CSV data that we get resulting. There's no way to distinguish from this first row or the second row. So this isn't the most appropriate use case for it. That said, if you go higher than 2 dimensions, this is possible to be preserved with just a little bit of work. So this third element here is another nested list inside of it. When we import this back, a simple map of to expression will interpret this string. Because if we look at the input form here, this is actually just a string. But we have the textual information to construct the data by using to expression. And this turns out to be a very good technique for a wide range of data. So, for example, sparse array. When we see a sparse array object, Wolfram Language internally knows the best way to turn this into usable CSV data. But the result here that we get isn't something that we can just call to expression on. Because we actually understand and look at the underlying data and dump that to the CSV file, we need to reintroduce this head of sparse array, but it directly interacts with the type of data that we exported. So you can still round trip high-level objects, even though CSV isn't necessarily a format that has the mechanisms to understand what those objects mean. There's a list of these types of expressions that CSV automatically recognizes in the scope section of the CSV documentation. If you're interested in looking at other data types, I recommend you look there. Now, one of these types that we don't have a representation for is graph. And you might have a collection of graphs that you want to preserve and import very quickly. In this case, we can actually just basically get the input form representation of these things. And yet again, this is nothing more than mapping to expression over our data and automatically interpreting all of these graphs. And it was very intentionally designed such that if you have some arbitrary expression, it should be able to be reconstructed. Now, in particular, dataset is one of those things that has such a complex structure that we had to really revamp how we can interact with it. And here's where I start losing my examples. Now, here's a really complicated data set. This data set, now if you're familiar with data set, the only way that you have headers, whether it be row or column headers, is with the structure of associations or nested associations. Now, once you have associations, you basically have given it a column header. Once you nest your associations, you have row headers. But it doesn't stop there. You can continue to nest deeper, richer associations within your data structures. And, well, you might be wondering, if CSV is two-dimensional, how could we possibly get back something at a depth larger than 2? Well, if we just grab a data set of the data, this isn't particularly useful to us. Not only do we have all these quantities that we can't do anything with, but the associations in here really aren't very readable. Now, we can grab the expressions. We can try the same technique that I just showed you, just to expression on the data set. But now we have quantities that are interpreted. But what happened to these nested associations? Well, part of this structure is that the data originally had headers, And in order to completely restructure it, we need to know how to turn some flat 2D data into something with a data set that already has the headers there. And this is built directly into CSV. The dataset support in CSV is very rich and very powerful. It can handle any wide range of ragged data that you can throw at it, whether or not the headers even exist. And even though these are keys of an association, it will construct the most meaningful missing representation for you. So in this case, we have a complicated nested dataset structure. And as you can see down here, this is completely equivalent when I import it back using header lines to automatically interpret the dataset headers. So now let's talk a little bit about upcoming updates to PDF. We've noticed that the PDF support that we have in the past is not as strong as we want it to be. And we have been working very hard to give it a complete overhaul. I can't say that this is coming in the next version, but we have a lot of progress and it'll be coming very soon in future versions. We plan to add full support for PDF 2.0, as well as low-level rasterization and image concepts. We also will introduce efficient partial access similar to CSV and Excel. This is something that we plan to actively maintain. This isn't something that we're going to write, put in the product, and leave. We're going to continue to add new features and make PDF support even more rich. But we are also going to maintain new versions of PDF as they come out. So if you look at 11.3, here's a PDF 2.0 file with all of these characters that it just doesn't know how to represent the constructs for. And I can show you one test that we have in a prototype version where all of these things are properly interpreted as their contents. So this will not be in 12, but very likely the next version after. I can't say for sure. So now we have CSV and PDF data, and we know that there are some low-level constructs that we can use to access parts of these data. How do we build an application where we can actually use the data that we're getting and do some important processing? So to start, one of the applications for maybe using partial access in PDF is you could do some kind of a search. So here's a PDF that I grabbed from the US Census Bureau. And this is talking about places with cities that have a population of greater than 50,000. And the first few pages will go up to 2012, but I'm really interested in 2017. So what I can do is define a very simple function which goes through and searches the PDF and actually gives the result of which pages it finds 2017. Now, for a slower operation like pulling in graphics and such, we can only extract the pages that we need in order to do our data processing. So let's take a look. Remember on page 1, it was just the intro page and it said something in the title about 2017. But if we start at page 18, we can see, yes, this is the data that has 2017. So, and what I'm trying to show you is part of the process of actually building the application. These are the kinds of things that you need to do is take a quick look and make sure that you have what you're looking for. And it turns out we do. Once we're satisfied, once we have the data that we need, importing just that chunk is the most efficient thing possible. So another thing that we could do with this is maybe look for particular data. So instead of just looking for the pages that say 2017, I'm interested to see something about maybe the state of Illinois. How many pages does it show up on that it is a city with more than 50,000? And here's those pages. But then we could do something even more interesting. Do a quick query to Wolfram Alpha and get the list of all 50 states. And all of a sudden we can very quickly build an association of pages that contain these data. And something that I found that was interesting is when we sort these, we see Vermont doesn't have a single city that has more than 50,000 people, which was surprising to me, and I thought maybe I did something wrong. But as it turns out, we asked Wolfram Alpha again. No, the largest city in Vermont is Burlington with 42,000 people. So the first thing that we're going to need to do if we want to get some rich processing and access parts of our PDF in order to do some analysis is trim down to the table that we're looking for. So just some very simple image take functions can get us very close to the data that we're looking for. So Here is just the import. We see that there's more things than we need, a simple trim, and now we're looking at just the table. You'll notice I didn't bother to trim the sides. It's very easy to detect the lines or any kind of grid in here. So this technique that I'm going to show you has been tested on a number of applications where there is a table of data in your PDF and there's some grid inside of it that you want to access the parts of. So basic text recognition is quite easy to do. And here's where I lost my dynamics. So we're looking at page 3 here, and this is a different document. Now we're just going to look at the populations for all the states in the United States, and we can see up here there's a row with the populations of the entire country. And we can take the original image, and the first thing that we need to do if we're going to detect these grid lines is determine exactly where they are by first finding the threshold that we need to binarize the image such that we get solid grid lines. And right as soon as we have solid grid lines, we can take a look at this and get an idea of the parameter that we used and actually, binarize that image. So now I have my set of images that are binarized. With just a few lines of Wolfram Language code, you can go through and find the peaks of the values in the rows and columns, and it very clearly points to exactly where each row and column starts. And we can highlight the image and see exactly the dot for each boundary. Once we know the coordinates for each boundary, segmenting the image is very simple to do by just making rectangles of the data. And you can see this list structure already contains the structure of the data. Now we just need to go from these images into something that's actually usable and computable. This is where we get into text recognition. So we have the segmented image, and this is as simple as text recognized mapped over this list of segmented images. All of a sudden, we have raw strings here of actual content that we can work with. But we're not quite there yet because we want to do some kind of numerical analysis on this data. And this is already very clean. In fact, the only thing that I'm seeing right now that needs to be adjusted is there's like a space in this one numeric value. And if we look at a grid of that, well, maybe not. So if we put this all together, this is really all the code that took. This goes from one of the images, grabbing the boundaries, segmenting the image, binarizing it, and recognizing the contents. So with this combined data that we get, we have everything that we need to start verifying that we have what we want. And now we have text data from the PDF. CSV isn't a format that can just be used to save your data. Import of CSV also has rich processing to interpret and understand things like headers. So we take our original image here, and this is just a screenshot from the original PDF. You can kind of see the numbers here. And so we want to make sure that we actually got the right numbers. One way that we can do that is by starting here with exporting the data to CSV, which just gives us strings. At this point, we've exported the data to a file, but CSV is just a text file anyway. We still can't do any computational processes on this. When you import CSV, though, it has the capabilities to turn strings into their numeric representations. Not only that, but features that have been recently released allow you to go directly to the data set so that you have named fields. So with header lines, we already have a data set that is entirely computable. If we look here, this is that first row and the rest of the columns saying that these are the totals that were originally in the data set for the United States. And if we look at these, because I had to magnify it, you can't see them together anymore, but I can tell you that they were correct, and I'll upload this notebook and you can definitely verify. Now, not only did we get that total from the line that we imported that said the United States, but if we actually sum the populations for each state, these are exactly identical. So we can be reasonably confident that this is exactly the data that we were looking for. It is already computable at a high level. And we didn't really need to do any processing. All we needed to do was understand the data from the format of CSV. So the last thing that I want to mention, and I didn't have quite enough time to put together an example for this, but some of the concerns with importing CSV data is, well, it is just a text file. You can really dump any amount of data to a CSV file. And this can get quite large. Pulling all of that content into memory isn't usually in our best interests. With a format like CSV, we have to do a little bit of due diligence in determining what the best approach for pulling our data is. Now, here's just a few things to consider when working with a lot of CSV data. The first thing is that you might want to buffer your data so that you only hold so many bytes in memory at one time while you're doing such processing. The thing that you have to understand about doing this is that if you're splitting on lines in order to buffer your data, there might be a new line within your data where all of a sudden your buffer stops in the middle of a row and you've destroyed your data. So before employing one of these techniques, what you should do is make sure that your data is free from these new lines. Not only this, but if your data contains many, many columns, but very few rows, this same technique of buffering by grabbing each line isn't going to be very effective. One other thing, and this could be a fairly general rule, you have to understand that the bytes that are on your computer don't necessarily immediately, it's not immediately obvious necessarily which characters they intended to represent because there are different encodings for such characters. In fact, if you have Unicode values, the most likely encoding that you're going to run into is UTF-8, and now each character isn't even represented by only one byte. By using a character encoding of ISO Latin 1, in any text application, you might find that you get a wonderful performance increase just because this can be interpreted directly as the byte string. So as you can see, there are a lot of tools that you can use to quickly and with high performance access CSV data and work between that and PDF. Thank you.